My knowledge of recent mind is that the partenariat è young ladies.
Yes, siren, which says that after diet in the short and that's
So, are there anybody who have not yet checked for
this kind of legend that is mild. Yeah,
Well, it is a
university.
Yeah, I was also for the moment
Yes, but here come the people's money, right?
I have reason about it. Shall we start? Huh?
C'è anche quello
Probably so this one.
Okay, so pleasure to introduce Dr. Bruno Bolzone. We're going to speak of recent developments of some nonlinear anisotropic diffusion equations. You can speak.
Yeah, so thank you very much for this very nice invitation, this very interesting workshop. So thank you, Matteo, and the other organizers for inviting me to explain to you a little bit about this long and fruitful project that in which Luis and my collaborator, Philomena Affairs, worked with in the last years. So in this talk, I'm going to show you a little bit the general context and the general results that we obtained in this in the setting of some diffusion, anisotropic diffusion equations. So I decided to present a talk with not so many proof, actually, without any proof. So just here to present the main results of this, actually the two papers that we did work together concerning this this context and this subject. So let me just start. So the introduction that I'm going to give you is just I'm going to present the main models that they're going to work with, that we described in the papers that I'm going to show you in a while. The second part would be dedicated to this important aspect concerning the determination of similar solutions in the context of anisotropic parabolic equation or linear anisotropic parabolic equations. The third part will be mainly dedicated to explain you some main properties of the models and in particular the existence and uniqueness of subsimilar solutions. This is actually one of the most important parts in which we dedicated we spend a lot of time in our work. And then yeah, I mean in the last part we are going to talk a little bit about this asymptotic behavior. So and about some little bit I'm going to show you a glimpse of some numerical studies in which some friends of us helped us with this. So let's start. So the main models that I'm going to present in this talk is first this one. You see, this is a kind of a version, an anisotropic version of the porous medium equation. You see here you have a different exponent with respect to each direction, each coordinate direction. I'm going to call it anisotropic fast diffusion equation because the exponent mi that you see here, the exponents mi that you see here are between 0 and 1. Of course, if all the exponents are equal, we recover the classical porous medium equation. In the case n larger than 1, or the fast diffusion equation when n is less than 1. So the assumption that I'm going to make here is then all the exponent mi less than 1, and this this guy here, which is the average of these exponents, must be larger than MC. MC is the classical critical exponent in the isotropic for the isotropic model. You see the classical critical exponent in the porous medium equation. So these are the two main assumptions that I'm going to take into account for the study of this equation. So this is the first model that I'm going to talk anisotropic fast diffusion equation. And there are some bibliography concerning this model. This is the first one is the paper that published in this year, obtained in collaboration with Juan Luis and Filomena Feo. And the other was concerns actually the same model. They were published some years ago. And there are also some recent developments, but in different range in this last paper with Sunshine. So the second model that I'm going to show you is this one. You see in the porous medium case and in the anisotropic for an anisotropic fast diffusion equation, you see that the degeneracy in U. You have the degeneracy here in the gradient, actually in each partial derivative. You see a different exponent pi with respect to each direction. And I'm going to talk this model as I'm going to refer this model as an anisotropic Laplacian equation. It looks like the Laplacian, but in the sense that if you consider that all the exponents are equal, you don't recover exactly the Laplacian operator at the right hand side. This operator here is called the orthotropic Laplacian. This looks like the Laplacian, but it is very different to the Laplacian. It's much more degenerated than the Laplacian. So there is a lot of literature concerning this operator. I'm going to show you some further examples concerning this. So what are the assumptions that I'm going to consider here? So we are still in the fast diffusion regime. So you have that all the exponents are between 1 and 2. And here P bar denotes the inverse average of the exponent, which must be much larger than this. This is the same exponent that you have in the classical isotropic theory, the classical critical exponent for the Laplacian evolution equation. Let me just notice that if you take this as assumption P1 and P2, then considering this together, this actually gives you this condition for the exponents, which actually tells you that the exponents are not too much sparse, and each other. And this is what actually many authors consider in the theory of these equations. By the way, they are called anisotropic diffusion equation with no standard Grove conditions. So So actually, as you see in our range, this condition actually it's always satisfied. So let me just show you a plot of the range that we are going to consider in this talk. So we actually in the discussion we consider this region between this red hyperbola, which is the red curve given by this condition here. We consider only two exponents of the two-dimensional case, and the p between 1 and 2. And then a lot of literature focus on this region here, because p where all the exponent pi are larger than 2. But anyway, we're going to restrict our consideration to this region here. Yeah, the literature. Yeah, there are a lot of papers that you can look at. I just restrict myself to list some of them. Of course, this list is very far from being exhaustive, and this contains both results concerning the elliptic theory and the parabolic theory. There are very nice results for general non-standard group conditions where all the exponents are different each other, the pi are different. And there are nice papers by my colleague Lorenzo Brasca and with the collaborators here. There are also this couple of papers concerning the same model, but in a different regime. So in this couple of papers, they obtain the existence of subsimilar solution where all the pi are larger than 2, and some Harnack estimates concerning the same model. For the orthotropic case, I recall the orthotropic case is when all the exponents are equal. This is a more specific model. There are some papers, very interesting papers that you can look at in this very brief list. So let's skip then to the one of the main aspects, so existence of similar solutions, and pass into similar variables. So one important aspect, so I'm going to consider here the anisotropic fast diffusion equation, and then a similar consideration can be done in the other model. So in this, since you have an isotropy with respect to each coordinate, when you look at the existence of such similar solution, you want to obtain a special solution to the main equation looking like this. You see here a different power of time with respect to each coordinate, where these exponents must be chosen appropriately. So what you do is actually to put, you replace you call yi as this product here. And then you put this guy in the special function in the main equation, and you obtain this equation here. You want to eliminate the time power, and this is eliminated only when you have this relation between alpha mi and ia. And of course, you are interested in having conservation of mass along the evolution, and by imposing this extra condition, you have an extra relation here. So you have a system of n plus 1 unknown, and you can solve it explicitly. Once you do that, you have the exponent alpha, which giving the exponent alpha, which are here of in front of as a time power in front of the similar profile of the decay, the time decay, is given by this guy. And if you call IA as a product of sigma I times alpha, then you have that sigma I must have this form. The sigma I, in some sense, controls the expansions of the solutions with respect to each coordinate direction. And the assumption that we made, that the second one giving telling you that the average of the exponents must be larger than the critical exponents, gives you that the exponent alpha in the time decay must be positive, and the two conditions together gives you that what you actually expect, that all these exponents sigma I must be positive. And then with all these choices, you have that the profile, the self-similar profile must solve this anisotropic, non-linear anisotropic elliptic equation in the whole space. Of course, you cannot, you can't expect to solve it explicitly, because in the classical case, you reduce to radial coordinates, but you have anisotropics here, and you don't expect to find explicit solution to this equation. Once the conservation of mass also must hold, it means that the integral of the solution must be equal to the integral of f, fixed to a certain m. So the question here is how to obtain the existence and eventually uniqueness of solution to this stationary equation. Going back to the classical isotropic case, you have this very classical form of the Barenblatt profile in the fast diffusion regime, the porous medial regime, where the constant here is actually can be determined by fixing the mass, and the condition when m is larger than mc ensures that this profile is integrable in the whole space. But as I said to you, in the anisotropic case, you don't get in principle any explicit formula for this asymptotic profile. But in any way, we were able to find results to prove results, giving you the existence of this self-similar profile by using, as I will tell you in a while, different techniques like fixed point techniques by using the Schauder fixed point theory. Yeah, you can do actually the same for the same argument for the other model, for the anisotropic Laplacian equation. And what you recover here by looking at a special solution in the self-similar form, you have that the profile must satisfy an equation like this, with this which is a nonlinear elliptic equation on the Laplacian type, anisotropic type. And in this case, of course, you are able to derive the exact form of the exponents alpha and sigma, which appears in this form here in this context. Okay, you can do the same. What are the Barenblatt profile for the? These are the Barenblatt profile for the Laplacian evolution. For the fast diffusion case, for the singular case, and for the degenerate case, and the condition that when p is larger than the critical exponent, it gives you guarantees that the profile is integrable in the whole space. Actually, we have more for this context. If you consider the orthotropic case, you can actually derive an explicit form of the profile. When all the exponents are equal, explicit calculation gives you the exact form of the profile. And you see the anisotropicity here appears clear in the exact form of the profile. So the profile here can be computed explicitly. Yeah, if you can look at all these results, these are contained in the paper and with Juan Luis and Filomena Ferrer in 2021. Yeah, what you have then in order to study the existence of a similar solution, a similar profile, rescale the equation, the main equation, by using some similar variables. And since you are in this anisotropic context, you must make this substitution here, like this, where the exponents alpha and sigma are before, and this with this transformation keeps the same and one norm through the evolution. And then what you obtain is that this function v is solves this very special anisotropic nonlinear anisotropic Fokker-Planck equation with this transport term. So if U is a solution to the anisotropic fast diffusion equation, then V given by this product of this power of time U satisfy this anisotropic Fokker-Planck equation. And you can do the same for the other model. If you take this anisotropic seminar variable, then this substitution here, then calling B the same guy as given by the product of T to the alpha times U, then this solves this anisotropic Fokker-Planck equation on the Laplacian time. And then now the study is reduced to the study of the solution of this Fokker-Planck equation. So the main qualitative properties of the Fokker-Planck equation that I'm going to show in a while. So let me just give you very briefly the main aspects of the main properties of the models, like existence of solutions of the weak solutions, and some properties like L1 and L infinity is smoothing effects and so on, just very briefly. And then we are going to focus on the existence and uniqueness of something solution, which really represents the core of my talk. As usually, we focus on the first model, on the anisotropic fast diffusion equation. As usual, the exponents are satisfied the first the assumption that I showed you many times. Then what you actually can prove by rather classical technique is that there is a unique function which is a curve from 0 infinity to L1, solving the main equation in a distributional sense. Other properties concerning this solution is that it satisfies this L1 and L infinity estimates. This can be proved by the classical Moser evolution techniques. And one very important aspect is the L1 contraction. So the map taking initial data associated to initial data, the solution of the equation satisfying the UC as initial data, generate a semigroup of L1 order contraction, in the sense that this inequality must be satisfied. This in particular gives you the maximum principle of the comparison principle of the solution. Once you start from an initial data which are less than the other, then this property is satisfied along the whole times. L1 contraction is very basic for all the considerations and the arguments that we will develop in our paper. So this concerns the first model. For the second model, for the anisotropic Laplacian equation, the existence in the L1, L2 settings can be recovered quite easily, because because this operator here can be viewed as a subdifferential of an explicit energy, and which are the sum of the integral of the pi power of the derivatives. So the existence is the existence of a solution, or the existence of a unique solution to the Gaussian problem is not a problem, because it can be recovered by the classical Bernoulli's theorem. If you want to enlarge the setting of initial data, then you can use the classical Crandall-Licker theorem. The Crandall-Licker theorem in linear semigroups. Of course, you must take care of some different details, but you can do that. So, like you have actually the existence of mild solution to the equation with initial or the Gaussian problem to the main equation. The L1 contraction also holds in this context. You can prove it. And also the L1 L infinity estimate decay given by in this form, in this context. Actually, it was proven in some papers in the past, but actually in our paper we were able to recover it by using symmetrization argument. This was very we were very happy that we could use symmetrization in this anisotropic context. It was very interesting because symmetrization gives you the way of how to skip many technicalities instead of using the classical Moser iteration techniques, you can recover it almost by free. So I'm not going to give you any detail concerning around the symmetrization techniques which allow to recover the L1 and infinity estimate. You can look at also in our paper with Luis and I think yes. So what are the qualitative properties of solution? Of course, you have since the models are anisotropic, what you expect is that when you start with initial data which are symmetric function with respect to each coordinate, and also you have that with respect to each coordinate is not increasing with respect to absolute value of xi, the coordinate you consider. What you expect that you have the same property for the whole evolution for all times. So using the Alexandrov reflection principle, you have that actually this holds. So if you say a symmetric function with respect to each variable, and it is decreasing with respect to the absolute value of this coordinate, then this property holds for all times. So the solution is symmetric and non-increasing. Yeah, and that's what you expect because of the nature of the model, which is the two models. The two models are anisotropic. This can be recovered rather easily by using the Alexandrov reflection principle. And so let's skip then. What I'm going to show you here is an acronym. So SSNI means separated, symmetric, and non-increasing. So it means that the solution is separated, symmetric with respect to each variable and is non-increasing to each variable. Of course, which is completely different with respect to the isotropic case in which you have the same property for all the directions. Let me just give you the main result that we obtained in this couple of paper that we brought together with Luis and Filomena Feo. Published in these two journals here, 2021, 2023. We were able to prove that for any mass, there is a seminal fundamental solution of both for the model of the anisotropic fast diffusion equation and for the anisotropic Laplacian equation with mass m. Moreover, the profile is respects the symmetry that I explained you before, in the sense that it exhibits the symmetry with respect to each variable and the monotonicity with respect to each variable. So the profile is as SSNI, non-negative function. And moreover, this is quite a subtle argument that in which we spend a lot of time, the determination of an explicit barrier. For both model, we were able to find explicit barrier, which I call GK, that actually gives you the spatial decay with respect to each variable of the single solution. Of course, if all the exponents here are equal here and here you replace yi by the absolute value of y, you recover the classical decay of the parabola solution for the anisotropic case, and the same for this. So this, as I'm going to give you to tell you in a while, this explicit barrier actually gives you the exact decay, spatial decay of the signal profile. So this, I would say that this actually represents the most fundamental results we obtain with this. I'm not going to show you any detail or proof, but one. Okay, so. Recall that what you want to actually do is to construct solution of the mass m of the stationary equation, of the stationary equation related to the Fokker-Planck equation derived by using the singular variable, and then very essential in our analysis will be to find a control from above. So determination of upper barrier of solution of the Fokker-Planck equations related to the two models. So the first important result concerns the control from above for all times of solution of the Fokker-Planck equations on the both models. Yeah, so this namely we were able to find conditions for which the solution V to the Cauchy problem related to the two models are below a certain barrier with capital G for all times. How do we determine the barrier of these two equations? Actually, by using explicit calculations, and we were able to make some tons actually of calculation in order to obtain this explicit form of the upper barriers. And you see here the integrability of these two special sub-solution of the stationary equation are integrable in a whole space out of any ball centered at the origin. And what you actually what we will actually take is a suitable truncation of the upper barrier. That will be the barrier which controls from above the solution of the Rescalet equation. And then, as you see, you see that this exponent here dictates and give you the rates of the asymptotics, the special asymptotics of the profile, the signal profile that I shown you in in some slides before. As I told you, I'm not going to give you any detail of this proof, which are quite rather delicate, but just one. So the existence of this profile actually is based on a fixed point argument, which is applied to the semigroup map associated to the scaled equation. But where you actually consider this semigroup map restricted to this very special class of initial data. The class of initial data are L1 and infinity, separately symmetric non-increasing. Actually, I fixed the mass equal to 1, but you can recover the whole mass by using some scaling arguments, suitable scaling transformations for both model of isotropic fast diffusion and isotropic Laplacian equation, and that all this initial data must be less than below a certain constant L. And you see this appearance of this as a suitable barrier here. So all the initial data must be below a certain barrier. And then once you prove that actually this semigroup map has a fixed point, what you actually obtain is that fixed point is the self-signal profile that you look for. Of course, there are some details, actually many details around this, many technical difficulties, but more or less the very core of the argument is related to this fixed point argument, in which we use the Schauder fixed point theory. So Schauder fixed point theory actually allows you to derive the existence of the self-signal profile. Okay, for both the model, isotropic fast diffusion and isotropic Laplacian, which with some difference because the models are related to each other, but they are quite different. So there are some differences in the proof. Uniform positivity. This is a very interesting aspect because what you expected then in the fast diffusion regime, you expected infinite propagation of positivity, infinite speed of propagation, and then the first thing that we were actually able to prove with the rather delicate techniques is that any self-similar fundamental solution is strictly positive, and it's also the self-similar profile is actually infinity function, very good regularity, and a positive function everywhere in the whole space. And we were also able to show this sharp lower estimate from below in the asymptotic behavior when the spatial variable y goes to infinity. And then by using some the comparison principle techniques, by taking the solution of the Cauchy problem to the two models, by using comparison principle with so comparing the solution with this similar solution that we were able to show that are positive everywhere, with rather delicate arguments, but actually the core of the arguments is related to comparison principle. We were able to show that any integrable solution with non-negative initial data are positive, and positive mass is strictly positive in the whole fast space. So we have infinite propagation of positivity, which is the very important aspect and very important property of the solution of each model, which is natural to expect. I didn't talk too much. Actually, I didn't tell you anything concerning the uniqueness of the self-signal, which is a very interesting aspect. And this has some differences between the two models. When you consider the anisotropic fast diffusion equation, you are actually you are able to see there is just one self-similar solution, by using a proper functional which is visible by the integral of the positive part of the difference between the two solutions. This actually is a rather classical Lyapunov functional, which is non-negative and non-decreasing in time. Since these two solutions are similar, what you obtain is that actually this along the flow this functional is actually equal to a constant. So the main argument, the main difficulty is to prove that this constant is equal to 0. This can be done by using maximum principal argument. So in this case, no problem. You have just one fundamental set similar solution to the model of the asymptotic fast diffusion equation. So there's a mass with this mass difference analysis is yeah, I mean it takes some details to obtain this, but it can be done. For the other model, actually, we were not able to obtain uniqueness in the whole regime in the whole general case. We were able to obtain this result only in the orthotropic case, because in this regime you have the operator is homogeneous. And then what you actually can use is Benney-Crandall estimates for the time derivative of the solution. And then you can actually treat the parabolic equation as a kind of elliptic equation having a source term given by the time derivative. And you can apply regularity results for elliptic equations, or with where the operator is given by the orthotropic operator, which were by the way known in the literature, and so we were able to then obtain by using this couple of results, Benney-Crandall estimates and the Lipschitz regularity, special Lipschitz regularity for elliptic equation for the orthotropic operator. We were able to see that actually solutions are Lipschitz continuous in space and time. Any strip of this form where tau is positive, and by using this property, then we were able to obtain this uniqueness result. What you obtain is that in the orthotropic case, where p is less than 2 and larger than the critical exponent, then the non-negative similar fundamental solution of the orthotropic equation, which is explicit, as I showed you in one of the first slides, is the unique fundamental SSNI solution of the equation with mass n. But unfortunately, so far we were not able to extend this kind of result in the more general case where all the exponents are different each other. So we have here the uniqueness result of a similar fundamental solution with this symmetry problem. Then yeah, just a couple of slides, and I'm going to end my talk. Asymptotic behavior. What you actually expect is that yeah, I mean we have for the anisotropic fast diffusion equation, you have existence, uniqueness of similar solution. What you actually expect is that this solution is this similar solution attracts any solution of the Cauchy initial data of the Cauchy problem, and that's what we were actually able to prove. If you consider the unique solution of the Cauchy problem U with the initial data U0 and integral in the whole space, then you have this asymptotic result. You have that U converge to the similar solution in the L1 norm. And also, if we consider more restricting condition of initial data, you can extend this convergence in the infinity norm. And so these results are rather complete for the isotropic anisotropic fast diffusion equation. In the other case, yeah, I mean the convergence when P is when in the intermediate case can be obtained by interpolation. In the case of the anisotropic P Laplacian equation, you have that the subsimilar solution is explicit, and then you still have the solution of the Cauchy problem converges to this subsimilar fundamental solution. And you can recover the norm with respect to uniform convergence, and also in LP case by interpolation. But yeah, I mean only in the orthotropic case. Yeah, we have numerical studies here. Felix helped us in seeing how the evolution problem show the appearance of an elongated profile. You start with a circle here, and you see that the profile of the subsimilar solution look like ellipses for various times. You see that time 2, 4, 8, and you have similarly similar behavior when you start with a square. Very interesting. There are many things to be understood in this concern that the anisotropic fast diffusion equation. There are many open problems that I end here. Many open problems concerning this the two models. Yeah, I mean the existence of a similar solution in the slow diffusion when all the exponents are greater than 1, and in the mixed case. Some MI in the fast diffusion regime, and others in the porous medium regime. What can be done for the anisotropic fast diffusion equation if you are in a very singular regime? Can we accept negative powers of the exponents? We still don't know. We don't know it yet. Existence of explicit solutions. I think should be no hope for that. And also this would be also interesting to study the problems in bounded domains, of course with suitable boundary conditions. And the open question, so this you know that the study of, for instance, of the fast diffusion equation is pretty related to some Gallardo-Nirenberg-Sobolev inequalities. How what can be said in this anisotropic context? This would be a very interesting aspect that would work to make some investigation in that direction. This is for the anisotropic equation of porous medium type, and there are similar, similar issues concerning the other models. So we were not, as I state you, we were not able to close the case where all the exponents are less than 2. For instance, uniqueness of fundamental SSNI solutions and the asymptotic behavior, and some similar issues to the anisotropic fast diffusion equation. So this list is rather big. Maybe it's bigger than I talk. Anyway, so thank you very much for your attention. So.
Ask some question. No.
Yes, you were mentioning interpolation inequalities, but would there be something also like mass transport with some anisotropy that would be reinterpreted? I mean, for the fast diffusion equation, that you can reinterpret the equation as a gradient field sample? But anisotropic distance or something like this that would
anisotropic distance with a kind of anisotropic version of the system distance. I didn't see anything in this kind of concepts in the literature. Of course, this would be nice to be investigated, but I mean, how to associate an energy to the anisotropic fast diffusion equation? That would be an entropy. That's the main problem, I would say. What is the entropy for that matter?
I mean, the only option that is reasonable at this moment is the orthotropic case for the pillar place.
So the pillar plate, which
You can get
Yeah.
anisotropic inequality.
for the pillar plation, you have a clear forms, it's actually the gradient flow.
But if the p's are different, you don't know what to do.
Yes. Yeah, you still have, you have some suggestions in that direction. Yeah, another one. Yes.
About rates of convergence toward the self-similar profile. I mean, in self-similar variable, are not translation enough to capture the lowest mode?
How much? What was the question?
Can you repeat? Sorry.
Well,
Can you repeat?
imagine that you are in self-similar variables, you linearize around the self-similar profile. Isn't it that the lowest mode will be given by a translation along one of the directions?
I don't know. Yeah.
Che rappresentazione ci sta?
Just to quote that, this, the anisotropic pillar placent, I think it was introduced in the book of Jacques Williams in 1969.
Yeah. That was great. Yeah.
It was for a long period. This is a type of pillar placent that we were using.
Pseudo pillar plash.
Yeah, well, you know, at the time it was only one.
There was only, yes.
No, I just also to quote that it is a question about the link, because you have a solution also for the P pseudo pillar placent equation, like in anisotropic, with like you may have solution which has u of t and x1 xn is a sum of ui of t and xi, each of them satisfying an equation in corresponding to xi, only one dimension.
Yeah, but they are not integrable.
No, they are not
That's
integrable. I agree with you. They are not
That's
integrable.
true.
In Rn, that's clear. They are not integrable.
Yes.
But you, at least, you have this type of object which exists. In the case that in a bounded domain, it can create problems.
Yes. Oh, bound domain. Okay.
For your opinion.
Yeah. It's
Okay. So I think we thank again the speaker. And go to the next speaker.
Oui. En fait, on peut les trouver.
I don't know.
It's just.
Thank you.
Okay. Oh.
Yes.
Yes, because.
Yeah, I know.
Oh my pleasure to introduce a new type of lecture, as we were doing in the last millennium. And you're going to speak of Riemannian and capacitory problem. Okay, you can speak.
Thank you for your introduction and also thank you for organizers. So it's my great pleasure to talk here. So this is my first time to come to Madrid and I really enjoy it. So today I talk about the capacity problem. So first let me introduce the problem. So let us consider some domain. So say omega 0 and I put here capacitor omega 1. And these have electronicity charge. Then, so I denote you this is potential, electronicity potential. So what is the situation? For the capacitor, so potential is always equal to 1. And on the boundary of omega 0, so potential is equal to 0. And then between omega 1 and omega 0, so there is a diffusion. So the situation is that Laplace of u equals 0. In omega 0 set minus omega 1 1. So we consider such a problem. And today we'd like to consider the shape of the level set. So here u equals 1 and on the boundary equal u equals 0. Then what is the shape of x? So u equals t. So if the situation is if omega 1 and omega 0 is both a ball centered at the same goal, then so super level set is just a sphere. So this is a simple situation. We'd like to consider the general situation. So something like this. So this is omega 1. And it is omega 0. And in this case, what is the shape of super level set or super level set? So it means that okay, L infinity and here is L 1. So we'd like to consider the shape of super level set. Then so I should say first, so B means here, so Kazuhiro Ishige there and Paolo Sarani from Firenze University considers the shape of this super level set when omega 0 and omega 1 are star shaped. So indeed, there is a theorem by, sorry, I don't remember the name. 1964. So first we consider a very simple situation. If omega 0 and omega 1 is the domain of Euclidean space such that omega 0 contains 0 and the closure of omega 1 is contained in omega, opposite, sorry. Such a situation. And they both are bounded and both are open. Maybe I should say here open. And assume that both are star-shaped about the origin. So this means that for any T between 0, 1 and for any point in omega I, TV again belong to omega I. So for example, convex set containing 0 is the shape set. And also such a star shape is also star shape. So because if we take here V, then TV belong to such a domain. So if we assume such a condition, then super level set U inverse, so open interval L infinity, here L it belongs to open interval 0, 1, is again started about the origin. So this is the theorem by Stuart, so 1964, and this is only consider the situation dimension 3, but this is also generalized for in general Euclidean space or more general capacitary problem. For example, one reference is sorry. About 1983. So, but they only consider the Euclidean space. Today, my talk is there are two theorems, so two characterization. So, first section, I'd like to introduce what is the definition of star shape in Riemannian settings. This is section 1. And then we show that the same theorem holds for in Riemannian geometry. But so we need some restriction. Then our Riemannian manifold satisfies kind of rotational symmetric condition. So this is section 1. So what is Riemannian star shape? And section 2, I talk about rotational symmetricity in Riemannian manifold. Symmetricity. In Riemannian manifold. So it is called warped product of open interval and sphere. I'd like to introduce two notions. Then finally, I state that our theorem. So such a statement holds for Riemannian manifold if Riemannian manifold is rotationally symmetric. So this is my plan. So then I would like to start with Riemannian star shape. To do this, so in my talk, always MG denote the Riemannian manifold. And always dimension is equal to n. So what is Riemannian manifold? So Riemannian manifold is locally. So if you restrict very small domain, then manifold is locally homeomorphic to Euclidean space. Yeah, space. So usually manifold is curved, so something like this. And today I fix a point P. Then we can consider the tangent space up to P. So I denote by TPM. So what is the tangent space at P? So roughly speaking, tangent space at P is the set consisting of the velocity of a curve. So, and this curve always passing through P, and we consider the velocity at the curve at P. So this is the tangent space. And if we take a velocity v, and if this is a Euclidean space, then you can consider the straight line, so passing through P and direction is equal to P. So this is a Euclidean notation. And this is denoted by exponential P of P v in manifold notation. Then manifold is complete, always exponential map. So this send the velocity at P tending to some point of N. So if this is the Euclidean space, this map is just P plus 3. So this is generalized to the Riemannian manifold, and the map is denoted by exponential map. And this is always well defined if Riemannian manifold is complete. So now, using this exponential map, we'd like to give the definition of a star shape of Riemannian manifold. So definition. So fix P and consider omega. So this is an open set and open neighborhood of P. So we say that omega is a star shape. So there exists S. So this is the set in tangent space, and I should say tangent space is isomorphic to Euclidean space. So and now we know that the definition notion of star shape in Euclidean space. So then, so this is a star shape about the origin such that if we restrict exponential map to S, then the exponential map is diffeomorphism that is so bijective and smooth from S to omega. So if we consider such a shape, this is S, so then if we map to such a domain. So if preimage of omega and the exponential map is star shape, we call omega the star shaped set. So this is our definition, not our definition, this is the usual definition in Riemannian geometry. So now, so this is well known. Sorry, is there some problem? Okay. Or
Question, you don't take geodesic flow?
not the flow. This is so
You don't take the geodesic.
Yeah, this is just this is the geodesic. Exponential is sorry. So this is the geodesic through at P with velocity V. Thank you. Thank you for your attention. You comment. This is just geodesic. Thank you. Then, so we give one characterization. So if omega is open neighborhood of O and there is some S ppm, this is open neighborhood of the origin and this has smooth boundary, not empty. And we assume that, so here exponential map P is gives a bijection from closure of S to closure of omega. We consider such a situation. Then, if omega is started, if and only if we have the following situation. So it is hard to draw a Riemannian picture. I just write down Euclidean picture. So here is P and here is omega. And if they have smooth boundary, then for example here, they so at the boundary Q is the point on boundary, then we have normal, autonormal vector, autonormal. And also we can, this is not so good. So we have geodesic from P to Q. So this line is geodesic from P to Q. Then here we have velocity of the geodesic line. So I denote it, so gamma Q dot 1. Then this picture shows that the angle between autonormal and the geodesic line is always less than 2 pi over 2. And the inner product at Euclidean space denoted by PQ. So this is just, okay. Maybe so this is, so this is Riemannian matrix. So if we consider the inner product of between autonormal and the velocity, then this is always equal to, always non-negative. So from the picture, you can imagine that if omega is star-shaped about P, then we have this direction. And conversely, if we have such a situation, then omega is star-shaped about P. So this is our characterization. And indeed, in Euclidean space, as far as we know, so this direction, so star-shape gives the inequality is known. And if we assume strict inequality, then we have opposite direction. But in our theorems, we show that even if this is equality, we have omega is star-shaped. This is our characterization. And indeed, in our theorem, when we consider the capacity problem, we don't use such a characterization. But anyway, so in this way, we have characterization of Riemannian manifold. So now I'd like to move to the rotationally symmetric in Riemannian manifold. So rotationally rotational symmetry. So this is called warped product of open interval and sphere. So as I said, so for any point Q in Euclidean space, so tangent space at M is isomorphic to Euclidean space as a vector space. But so usually, so if we consider the Riemannian manifold, so each tangent space has inner product denoted by DQ, GQ. And so in Euclidean space, of course, there is a standard inner product. And usually this is not isometry. But if there exists some function lambda, so this is 0 to R and positive function such that each tangent space is isometric to Euclidean space inner product times some function lambda of dpq. So dpq is the distance between p and q of square. So if we have such a situation for any q, here q is the element whose distance from P is less than R. And here R is 0 to infinity, and also infinity is okay. If we have such a situation, we say that the ball BPR is rotationally symmetric. And in what follows, we consider only such a situation that if there is a ball and the ball is rotationally symmetric. And what is the rotationally symmetric ball? Of course, one typical example is Euclidean space. So Euclidean space is always rotationally symmetric. Example. If M is Rn, then we can take lambda is just a constant 1. And next typical example is sphere of radius R. And in this case, lambda is given by cosine of T over 2R times 2. And how do we derive this such a function? So if we consider Euclidean standard inner product, then if we consider, so this is Cartesian. And if we consider polar coordinate, so this is denoted by dt square plus t square and standard metric on sphere. And on sphere, so if we consider polar coordinate, then so radial direction is same, and here we have such a function r times sine t over r square and degree Sn minus 1. So how do we derive this? So because if we consider the sphere like this, so here is the origin and the radius is R, and if we fix North Pole here, E plus 1, and if we consider point P, then if this distance is equal to T, then this angle is T over R, and then this length is R sine T over R. So if we consider the polar coordinate, then the effect of length is not T itself, R sine T over R. Then here, R sine T over R appears. And if radius goes to infinity, then sphere approximate to the Euclidean space. And then this goes to P square, same as the Euclidean case. So this is a rotationally symmetric. And of course, hyperbolic space is also rotationally symmetric, but I don't give explanation here.
Just a question. In your notation, VPR is a geodesic ball?
Yes, geodesic ball, open ball, metric ball, thank you. So if we consider the hyperbolic space or Euclidean space, then we can take R to infinity. But for sphere, R is at least R pi. So now I'd like to state our main theorems. So let us consider omega 0 and omega 1, which is the open set in Riemannian manifold, such that first situation is the same. So omega 1 contains point P, and the closure of omega 1 is contained in omega 0. And we assume that this is bounded. But we don't assume omega 0 is not bounded. But if the boundary of omega 0 is not empty, so empty is okay, but if it is not empty, then we assume that not smooth, so I explain again later. So, and omega 0 is contained in PPR, and this is rotationally symmetric. And assume that omega 0 and omega 1 is star shaped. And we also that, so omega 1 is star shaped, so then there is a S, this is diffeomorphic to some tangential space at P. We assume that so such a diffeomorphism is also bijective even if we consider the closure of S omega. No, sorry, omega. omega zero. So this is bijective. Because if we consider the sphere and omega zero is just sphere and taking 1 point, so then this is star-shaped, but in this case, the boundary has strange behavior. Boundary behaves strange, so then we'd like to avoid such a situation. And let us consider the capacity problem. That is, so U equal 0 on closure of boundary of omega 0, and this is equal to 1 on the closure of omega 1, and Laplacian of U equal 0 in between omega 1 set minus omega 0, such a situation. Here is omega 1 and here is omega 0. Then, as I said, so always super level set of U is star shape. About T. So this is our main theorem. And I give the key of the proof. So T is that, so if we consider the function large U, this is defined by U compose exponential map P inverse. We consider such a function. Then this is the function on the tangent space. And the tangent space is isomorphism to Euclidean space. Then we can consider U as a function on Euclidean space. And for example, here, strictly speaking, Laplacian is with respect to Riemannian manifold. But now we can rewrite the equation of small u as the equation of capital U. Then we have first U equal 0. No, 1. 0 on boundary of x0. And what is x0? So x0 is the pre-image. So this is not true, but roughly speaking, this is pre-image of omega 0. And of course, U equal 1 on x1 closure. And the x1 closure is a pre-image of exponential of omega 1. And finally, what is Laplacian of M of U? So this is Laplacian of Rn U plus n minus 2 times gradient of logarithmic of lambda. So what is lambda? Lambda is, I introduce lambda when we talk about rotationally symmetric. And Laplacian, so here, no, Laplacian, not Laplacian, sorry, gradient of U equals 0 in x0 set minus X1 closure. So in this way, we can translate an equation of Riemannian manifold to equation of Euclidean space. So then we can use a technique of Euclidean space, and indeed we use theory of viscosity solution, and we show that. So what is the goal of our theorem? So our goal is that super level set of capital U is star set about the origin. And we show that by using non-Euclidean technique. And this is our theorem, and indeed, so in our paper, so now just preparing, we consider more general operators here, but this is only Laplacian. So I think this is the time, so I stopped my talk here, so thank you for your attention.
It's very nice lecture. Old patient, but very pleasant.
Thank you.
I have a question, which is take an example M to be the sphere, Sn minus 1 or Sn. What is lambda in that case of the sphere? What is going to be the equation?
Okay, so if we consider, so you mean that if you consider M
To be Sn.
equal S minus 1, so yeah, indeed, so strictly speaking, we don't use here exponential map, we use stereographic.
Yes, so it is a stereographic project.
Yeah, then in this, if we use stereographic and this is 1, then this is just 1 plus 2 square 2.
Okay, but there is no gradient. It is just a multiplication of U, no? There is a gradient which appears. What is going to be the new equation?
So this is lambda, sorry, lambda. Here is lambda.
So it's lambda.
Lambda, sorry, this is not size. If we consider the sphere, we need here is lambda. Then so in the case that sphere lambda is given by such a function. And here X is the result of stereographic projection.
Okay, but in that case, you have the conformal Laplacian.
Yeah, this is conformal Laplacian, but there is, indeed, if dimension is 2, then conformal factor is vanished. But so because we consider the general dimension, then there is a conformal factor.
Okay. And on hyperbolic space, what is your
If we use Poincare disk model,
Yes.
then so this is just minor.
Okay. Okay. So are there other questions or comments? So we are going to thank you again.
Thank you.
You know, we have lost the habit of this type of.
I'm really bad at make
Really